I thank the organizers for the invitation to speak here, even though it's not really on topic for what the topics of the conference are supposed to be on. So, I mean, I guess until a few years ago, nobody thought of looking for interesting operator algebras on LP spaces where P different from 2, and probably people assumed that there weren't any. It turns out that there are some, although the theory is still very much in its infancy. Most of the things that have been looked at so far are norm-closed operator algebras. Since this is a conference or program on phenomenon algebras, I figured I should figure out something or other about, say, weak operator closed algebras on LP spaces. So the results, what I have, I mean, even just started looking at this about a little bit over a month ago. Things are very preliminary. Some stuff is already known, and I'll mention that. And I'll tell you something about what we think we have. I should mention that a fair amount of this is joint work with my former student, Eusebio Gardella, who's also looked primarily, he's done various other things, but also looked at sort of C-star-like operator algebras on LP spaces. So let me tell you, since the C-star theory has been done much more, let me at least tell you more or less what's happened there, or is happening. There's no adjoint on LP, so we don't know we don't have the right definition of an LP like C-star algebra or an LP analog of a phenomenon algebra. We have some examples. We have some conditions which we think they should satisfy to be C-star-like or phenomenon algebra-like. The conditions are not consistent with each other, and there are variants of them. So we have to rely, at least for now, on, we hope we recognize one when we see one. To find the right definition, or maybe several of them, is still one of the unknown things in the theory. But let me put up with the C-star like operator algebras on LP spaces that have been studied. So first of all, I should put C of x, although of course this is the same. As the C-star algebra. Right, you represent it by multiplication operators on x with a suitable measure. Then LP UHF algebras, more generally LP AF algebras. Full and reduced cross products, including group algebras. This turns out to work much better for discrete groups than otherwise. Okay, Cuntz algebras. The triplets algebra. And a few others. But this is sort of the main examples that we looked at so far. I should say, I guess I might as well now mention there are some choices about how you might want to approach these things. So here, and making different choices here quite possibly leads to other interesting theories, although possibly somewhat different. The only reason I'm using these choices is that they do seem to lead to an interesting theory, not to exclude other possible choices. So one of them is its LP spaces up to isometric isomorphism. There are two categories of monic spaces that people in monic spaces work with, and one of them, the morphisms, are bounded linear maps, and the other one, the morphisms, are contracted linear maps. The theories are quite different. The algebras up to isometric isomorphism. P is in the range 1 to infinity and often not equal to 1. Not going to say anything about P equals infinity, still less about P less than 1. What was the other thing I want? And, oh yes, and LSP spaces are commutative LP spaces. Maybe one should look at algebras, for example, operators acting on LP of a phenomenon algebra with a trace with respect to the trace. So it's a different space. There'll be different algebras, more of them. But that's certainly a direction one could in principle go. Let me put, before going to the examples, a couple of, or sort of one of the key technical tools. And this will tell you, first of all, how much more rigid things are on LP. And nevertheless, maybe somewhat surprisingly, this technical tool allows one to do some things which are somewhat similar to what one does with C-star algebras. It's Lamperti's theorem. And I won't say the theorem in general. One word of caution, the theorem in Lamperti's paper is not quite correctly stated. But it's about isometries on LP spaces. And I'm really concerned mainly about the invertible ones here. And so if mu is a sigma finite measure, and S in boundary operator of LP of x mu is, the theorem covers more general things, but this is the one I actually want, it's easier to state, is an invertible isometry. Then S is a product of two things. Much more rigid than unitaries, and here, of course, P is not equal to 2. And in fact, the right condition here is P is in 0 to infinity, but not 2. One of them is multiplication by a function in L infinity with absolute value 1. And the other is basically comes from automorphism of the measure space. Let's see. Comes from a measure class preserving automorphism of the space. Well, it should be a slight generalization. I mean, in fact, what you have to do is to allow an automorphism of the sigma algebra, which preserves the null sets. And in the general situation, it seems to be unknown whether that actually comes from the map on the space, although it is true under some conditions. I'm going to assume everything is separable, and so that won't actually be an issue. And of course, when you write down what the map actually is, I mean, if it's a map from x to x, which preserves the measure class, then to get an isometry, you have to put in some Radov-Nikodym derivative to some suitable power. won't write the formula for it, but and so one consequence is seen in rigidity. So if P is in, this allows 1 infinity but not 2, and A in L counter operators in LP of x mu, or using the finite, is norm closed, is a unital norm closed subalgebra, then there is a largest C of x in it. C of I shouldn't put y here. There is a largest subalgebra isomorphic to C of x for some x. In other words, it contains all the others. And how do you see this? Well, to see this, I'll just give you the basic idea. So if, say, C of x is included into A, included into counter operators in LP of y nu, I should have changed the name of the measure too, sorry, nu, then for f in C of x real, lambda mapping to e to the I lambda f is a norm continuous path of invertible isometries. And in Lamperti's theorem, if the path is norm continuous, the second factor has to be constant along the path. So the path has to consist of multiplication operators. All right, so for all you people worrying about uniqueness of up to conjugacy or whatever of Maxwell-Abelian subalgebras in various factors, it's dramatically simplified in some sense. Well, if you look at this kind. Okay, so now let me start off by telling you what happens for LP versions of type 1 factors. So this is sort of, in some sense, background. Most of what's here was already known, but it should provide some indication of what to expect. And then what I will tell you is what we have so far discovered about LP analogs of type 2-1 factors. And some of this stuff will be shockingly strange, and some things will nevertheless seem to work right. And besides that, there's all kinds of questions. They've only been working on this for about a month. There's lots to do. So first of all, let me look at the finite case. You have the n by n matrices. Write it like that. Is just n by n matrices normed as acting on little LP of endpoints in the obvious way with counting measure here. Well, I mean, you know what the algebra is. If you ignore the norm, it's finite dimensional. You know everything about it. Okay, let me tell you what the isometry is in it. They're not all the unitaries. They are only the complex permutation matrices. So I have something like this. Well, I have a non-zero entry only at, say, k, sigma of k, with sigma 1 to n with self-bijective, say s, and the absolute value of s, j, and k, sigma of k, is 1. So it's a permutation matrix, except I allow out complex numbers of absolute value 1 instead of just ones. That's all of them. By the way, when I tried to compute the K-theory of the Cuntz algebras, I first tried to follow Cuntz's original proof, and it relies on connectedness of the unitary group. And it turns out that you have to use the isometry group instead. The isometry group is not connected, so the proof falls apart. I did something else instead, used cross products. The other true thing I should say is that for different values of p, these things are not isometrically isomorphic. All right, let's see. I guess I can use this board. Right, point infinity.
And if you put a different measure than the measure that's the same,
It doesn't matter.
You get the same algebra.
Yeah. The underlying space is isometrically isomorphic. Yeah. So as long as the measure is just equivalent, then multiplication by a suitable Radon-Nikodym derivative uses an isometric isomorphism between LP for one measure and LP for the other one. Yeah. So there really is only one of these for each n. For each n and p. And similarly, for infinite dimensional LP spaces, there are not very many, but there's more than one. Let me tell you first of all about that operators an LP of z, or LP of n, doesn't matter. Counting measure or an equivalent measure, even if it's not equivalent, as long as the measure is infinite support, you toss the rest of the points, and you're fine. All right, so what sorts of things happen? Well, so first of all, I should tell you, right, on dot operators in Hilbert space or in C-string algebras, you have idempotents and you have the good idempotents, which are projections. And moreover, in any C-string algebra, every idempotent is morphonomically equal to a projection. You have to use functional calculus for it. Continuous functional calculus is good enough. So here, in general, the good idempotents seem to be what are called the Hermitian idempotents. I won't write down a definition. Projections are Hermitian. In a C-star algebra, an idempotent is Hermitian if and only if it's a projection. But in that operators an LP of y nu with nu sigma finite. Well, the good ones are associated with invertible isometries, and therefore they have to be multiplication operators by something. They are multiplications by characteristic functions of subsets of E for E in Y measurable. So same kind of rigidity. Okay, so what happens here? Well, okay, you know what they all are. And it's obvious what they all are. And it's obvious that any two of them of the same rank are similar and so on. So for Y being just integers, it's clear what they all are. And that they are similar. Say E and F. Similar via invertible isometry. If and only if rank of E is rank of F and rank of 1 minus E is rank of 1 minus F. And similarly, the condition for Murray-Benarm equivalence. Isometric. It's just rank of E equals rank of F. Okay, what about the other ones? So there's a fact. Easy to prove based on stuff that was already known, but I don't think anybody really paid attention to this before. If E, an operator, an LP of Z is not idempotent, then it is similar to a Hermitian one.
Would you define the notion of Hermitian?
No, I didn't, but I could. Want me to put it up? Sure. I basically said this is the good kind, but the definition is well, there's several equivalent conditions, of which the following one is probably the I should go further. So where's the eraser? Here. So it's not the original definition, but this one equivalent condition. So I take C direct sum C mapping to A. So this works for any unital Banach algebra. By lambda 1, lambda 2, mapping to lambda E1, that's right, 1 E plus lambda 2, 1 minus E. This is supposed to be a contractive homomorphism. Unless one of those things is 0, that actually means it's isometric. There's other conditions involving things like the norm of x of I lambda E being less than or equal to 1, and some condition about the derivative of that at some place or other.
Is this equivalent to being self-adjoint in a C-star algebra case? Or is it
Yes, and a C-star algebra is equivalent to E being actually a projection. And in fact, there's a general notion of a Hermitian element for which this definition doesn't work, but for which other ones do. And in a C-star algebra, that is also equivalent to being self-adjoint, just for an arbitrary element. But one condition is that lambda mapping to e to x of I, so a x I lambda a, that should be, these things should all have norm 1. Okay, so one thing which I did not write in my notes, that perhaps I should have, is that right, you know that even in a usual C-star algebra, every element is a linear combination of, I think, 4 unitaries are enough. Down of operators on little lp is not the norm closed linear span of its invertible isometries. You can, with some work, prove more or less directly. Write down something which, well, write down something you can show is not in the norm closed linear span of the invertible isometries. It's worse if p equals 1, where you can find a rank 1 operator that's not in the norm closed linear span of the invertible isometries. That doesn't happen for p not equal to 1. Yeah, oh yes, I was going to say, so this depends on some fact about Banach space theory. Basically, it comes down to saying that every complemented subspace of little lp of z is isomorphic to little lp of z. So, I mean, that's an old theorem, but took some work, and with that, it's not much more to get the result, which I actually put out. But there's more than one LP space. Let me just predict this to capital LP. Well, so assorted things go strangely. If p is not equal to 1, then there are many norm closed ideals, not just the compact operators, not just the closure of the finite rank operators. What happens to the idempotents? So there are no finite rank Hermitian idempotents. They're certainly finite rank idempotents, but they're not similar to Hermitian ones. Even infinite rank idempotents. So there are many examples of infinite idempotents. E such that rank of E and rank 1 minus E are infinite. And E is not algebraically Mervin equivalent to, in particular, not similar to, the Hermitian idempotent. At least for p not equal to 1. and the point is, I think it's open if p is equal to 1. But the point is that the range of E can fail to be isomorphic to an LP space. can fail not just to be isometrically isomorphic, it can fail to be isomorphic at all. In fact, there's now uncountably many possibilities you could have here. And if that doesn't happen, then it's certainly not equivalent to the multiplication by the characteristic function of something. The K-theory comes out right. I mean, if you, once you take, well, I mean, of course, the K-theory of the whole thing is trivial, so it doesn't really help you very much. Yes?
Is it easy to, I mean, that counterintuitive fact that you just said, like, is it easy to explain why that's the case?
Not that I know of, but I have to warn you, I am not, don't know that much about Banach space theory. This is one of the things you actually do have to know about to work on this. And I don't know much myself, but I've been getting lots and lots of information from Bill Johnson. So most of what I know about Banach space theory comes from him. And yeah, I don't know exactly. Well, okay, so there are some things that you can do. There's some construction involving, what is it? Identically distributed normal or something random variables, which gives you a subspace, a complemented, I think, subspace of this, which is isomorphic to little L2. And this apparently is relatively easy to do. Okay, when the idempotent on that, I mean, if I'm right that it's complemented, I don't remember for sure. The idempotent for that one is certainly not going to be equivalent to multiplication by anything. But there's apparently a lot more. There are general theorems known about when some spaces of this type or that type embed in others or as complemented subspaces or whatever. So a lot of this is fairly old. Is there anything else I wanted to mention about that one? Oh, yes. Well, as you can already tell, these are not isomorphic. What I told you basically says they're not isometrically isomorphic, but in fact, and this actually is new, as far as I can tell, there is no non-zero norm continuous homomorphism from boundary operators on capital LP to boundary operators on little LP. Even if I forget about asking to be isometric, I completely ignore the weak operator topology. When we look at the norm topology, and of course P is not, or P not equal to 0. There's no non-zero norm continuous homomorphism. There is also, and I'll just briefly mention these operators on LP of 0, 1 disjoint union Z, or use finitely many points. So the LP spaces, so these things are isomorphic, but not isometrically. To LP of 0, 1. So you will still have all kinds of, these don't have rank 1 or don't have norm 1, all these idempotents here, but you'll get a different list of which things are permission idempotents, because here, for example, you have permission idempotents of all finite ranks as well as infinite rank ones. And we really haven't looked very much at this space yet. Are there things we don't know?
How does this non-isometric isomorphism between two LP spaces come about? Can one describe
Yeah,
it?
so it means that there's an invertible linear map, but it doesn't preserve the norm.
Sure. But can one write it down, or is it some abstract existence?
Can you write it down? It's not completely, I don't remember exactly how to do it.
I guess the direct sum
But-
of capital LP and little LP is isomorphic to.
Yeah, I mean, I think what you do is I mean, if you can take out a rank 1 projection from capital LP of something, and I think what's left over is still basically this isomorphic to capital LP of something. Now that's not in general true for product spaces. They're not in general isomorphic to their codimension 1 subspaces, but it is true for LP. And then once you have that, you can at least iterate it to get finitely many of them. And if you have suitable norm control, which I think you probably do, then you can get this. So,
Okay, thank you.
so that I think is how it works. But yeah, yes, the right person to ask this is Bill Johnson, who is not here. Other questions before I go to type 2? Howls about rage? All right. So I'll follow 3 constructions. 2 1-factors. 1. Take an extreme trace. Rational state. And I'll take second commutant. 2. Group measure space construction. So here I'm interested, I say especially, algebra. And I'll call the LP version. I'll just call it WPR of GX. And so G is discrete, countable. X mu is a probability space, a standard probability space. And the action is free and ergodic. I mean, I'll mention this in some cases in general, but those are the usual assumptions. And 3 is you take the group phenomenon algebra of an ICC group. Infinite conjugacy classes. There are lots of others. Those are the ones which seem the most accessible here. If at some point somebody has suggestions for other ones they'd particularly like to have looked at, I'm happy to take suggestions. Okay, so what happens? So it's easy to write down analogs of the second and third ones. Third one, this is actually being looked at by homoeconomic analysts. We'll call it PMP of G. Whether the group is any discrete group. Any, let's say, countable discrete group. It apparently stands for pseudo measure or something like that. I'm not sure. When I'll be writing things, I'm not using this notation, but I'm not going to worry about that here.
So what is this? Can you define it more precisely?
Yeah. Yeah, I should be careful here because I do want to say that. So what is it? I let G act on LP of G by the left regular representation. and I take weak operator closure of the linear span. And for that one, I simply write down the usual phenomenon algebra version, only I put LP everywhere. So for 2, you act on LP of G cross X with the same formulas as for the phenomenon algebra case.
So 3 is a special case of 2, is that right?
Yes. If I take X to be a point.
Okay.
But of course, it's not free energetic.
That's good.
Yeah, so sometimes I want to refer to the general versions of these with no assumption in the group, without any assumption in the action. But as constructions of factors, I want free energetic here to separate it from those ones. So you'll see why. And then take weak operator closure. So these are the algebras you get. Okay. I'll come back to one in a bit. So what happens is that, analog the non-algebra result is that if G1 x1 and G2 x2 are orbit equivalent, are measurably orbit equivalent, then you get the same algebra. By the same proof. You'll check this. I didn't go through details, but yeah. It doesn't depend on what P is. In particular, let's see. So as long as G is amenable and the action is free and ergodic, I always get the same algebra. Of course, it should be infinite, but the free ergodic action of a finite group will give you the n by n matrices. So this is like the uniqueness for the hyperfinite 2-1 factor. Now, if you try to do this kind of construction, well, it's not quite clear what the GNS representation should be. I mean, there are things you can write down which are sort of like this, but which have the disadvantage of landing you not on an LP space, but on something called an SQP space, which is more general. On the other hand, you can take your tracial state on a UHF algebra. You can try to work out what the Hilbert space you're actually getting, a concrete description of it in terms of L2 of something. You replace 2 by P, and you can write down some algebra. Well, it's easiest, it seems you get the same thing. Not all details checked, but sure looks like it. So for 1, what we just do is we take, so for tensor product from 1 to infinity of m dn, okay, you simply choose groups Gn with cardinality of Gn equal Dn, and you take G is the direct sum of 1 to infinity. Gn, well, I mean, it's sort of It's improper notation because it didn't assume these were abelian, but it's the same thing. And x is just the product with the product of normalized counting measures. And then you do measure space construction. And that gives you it turns out the same thing in the for Neumann algebra case. And so this tells you how to actually do this, at least in that particular case, without actually going and writing down some complicated, right? When you write down the actual Hilbert space, you find that it does indeed come out to be G cross X, except that it comes out in a twisted way. So it's a bit awkward to write down. So in particular, this also gives you the LP version of what I think is the hyperfine actually one factor. So what are some good things about this? Well, here are things that we probably have. Again, not all details written down on these. So, for this case, so it's over here. Unique weak operator continuous tracial state. That should actually work even if the group is not amenable. Unique norm continuous. Don't know. No non-trivial weak operator closed. Ideals. Norm closed ideals, we don't know. Rest of them. For lambda 0, 1, there exists a Ramish idempotent with trace lambda. If two Ramish idempotents have the same trace, they're similar. Tau of E is tau, I should call it the name. Right, E is similar to F by an invertible isometry. So these kinds of things we have to do explicitly. There's no general theory that we know of. And so you have to do a bit of work. Group of invertible isometries. Consists of products of functions in infinity of x mu. So this is the measure space where you're acting, not the space in which the algebra actually lives. With absolute f equal 1. And automorphisms of the measure space. So measure preserving and since this is a standard measure space, I mean, they're all the same, so you get the same automorphisms, no matter which one you use. Standard non-atomic. And there was one more. Oh yes, and right, you saw there was a difference between little LP and capital LP. So there is no isometric weak operator to weak operator homeomorphism from its algebra to any subalgebra of the boundary operators on little LP of Z. Well, suppose I relax the conditions rather dramatically, I can insist to be contracted and non-continuous, forget about weak operator topology at all, then probably there's still no homomorphism. And just for contrast, the LP UHF algebras do act on little LP of Z. They're isometric isomorphic to norm-closed subalgebras of this. How can you tell there's nothing weak operator continuous? Well, you look back at the consequences of Lamperti's theorem, and you see that the multiplications by L infinity of things in L infinity of x, well, that's a subalgebra isomorphic to C of something. So they would have to go to multiplications by things in little L infinity of Z. Only now you have weak operator continuous homomorphisms from L infinity of Z to the complex numbers, but not from L infinity of x mu when x doesn't have any atoms. So you see, some of these things are relatively easy. Okay, so now,
In your long list, when you prove 4 about the idempotence, do you classify them like in the case of bound operators on little L2?
yeah, because since they're Hermitian, they have to sit inside, it turns out, the L infinity of, again, assuming free and ergodic, the L infinity part, I mean, it's a maximal abelian subalgebra, so it's the maximal copy of C of Z, and so they're all in there. So they come from characteristic functions of measurable subsets of the original measure space on which the group acts, and that's all.
Okay. So that, and
Yeah.
what about idempotence Carnot Hermitian? Are they similar to those?
We don't know. Yeah, so thank you, actually, I nearly forgot to say that. So in 4, so, I mean, for example, can you find some of these idempotents whose ranges are not LP spaces in this thing? I suspect the answer is no. After some thought, but I don't really have any ideas toward a proof, but at least sort of heuristics suggest that, in fact, every idempotent is similar to one of those. But certainly no proof. Okay, so I left off ICC for a good reason. So it's a theorem already known. G1, G2, countable groups. Don't have to be ICC or anything like that. PMP of G1 isomorphic to PMP of G2 isometrically. right? In the phenomenon case, countable amenable ICC groups are always the same. Sorry?
P not 2.
Yes. But p equals 1 is allowed. How do you prove it? Well, I mean, this isn't my theorem, was done earlier, but basically what you do is you find what are all the invertible isometries in this. And it turns out that they are the group generated by multiplications by functions in little L infinity of G, and the group elements. So you look at the norm-connected component, take the quotient by that, it's G1 or G2. None of them is WPR of Gx for free ergodic action. You asked about idempotencing here. So there are no non-trivial permission idempotents. If G has no torsion, it's not clear if there's any non-trivial idempotents at all. This might possibly come out differently between p equals 1 and p not equal 1. And finally, one thing which you may have been wondering what happened to. What fundamental theorem of phenomenal algebras did I not mention yet? Double commutant theorem. So it's known if G has the approximation property. It's known that that PMP of G double prime equals PMP of G. And you can get this for the group measure space construction with the same group. In general, it's open.
What is the approximation property?
It says that, so amenable groups have it. It says that you can get the constant function in the group as a limit with uniform convergence on compact sets of, positive definite functions which are contained in A of G, which is the pre-dual of the phenomenal algebra of G. So it's one of these things. It's weaker than amenability, but it's whereas SL3Z doesn't have it. And in fact, SL3Z is being suggested as a possible counterexample, but nobody knows. So sometimes you have double commutant theorem, sometimes you don't know. Various questions. I should mention at least one, and then I think I'm supposed to stop. You take this one, the one which we think looks like hyperfinite 2-1 factor. What subfactors does it have? Does it have all of the subfactors that you're used to in the phenomenal algebra situation? And probably things you can get is by taking double commutants of AF algebras probably actually work. So So the guess is that it requires some work to do, that lots of them are in fact present there. But that's one direction where nothing is actually yet being done. There's several other questions around, but I think I'm over time, so I should stop. Or howls of outrage.
Okay, let's start the quiz again. So there's no break.